Okay, so case study time. So in this week's lectures, we talked about this poison example. And again, I apologize. This is a horrible thing, but it's a very simple example. And what it was is they were looking at how they could treat certain poisons in animals. And so what they did is they took animals, they were exposed to one of three different poisons, and then they were given four different treatments and worked out the survival time. And they're trying to work out what would help them survive. So, as always, we've got our Markdown. Let's build it up. So, I'm going to have tidyverse. We don't need tidy models. That's just my default. I've also got the GGLM, so we get the nice plots. I'm using my Pacman package. Load that. Good to go. So, the data is in a package called rfit if you want to get it. And so, I'm asking for the box cox data in the package rfit. Now this is a data frame and I prefer them to be tibbles, so I'm going to convert that to a tibble and have a look. So let's have a look at what we've got. So we have the log survival here. We have which poison you've got and which treatment you've got. And altogether we've got 49 rows. So it's hard to actually see what's happening there. So what I'm going to do is I'm going to do a quick command. I'm going to take the poison, I'm going to count the poison. You'll see here that we have 16 of the rows are poison 1, 16 of poison 2, and 16 of poison 3. And I just think it's going to get very confusing if I have poison and treatments the same names, everything. So what I'm going to do is I'm going to convert it. And whether it's a 1, I'm going to call it A. Whether it's a 2, B, C, etc. So that's what this command's doing. It said taking the poison, create a new column called poison. And the case is when poison equals 1, call it A. When poison equals 2, call it B. When poison equals 3, call it C. And if you get all the way to the end and you're not called anything, call it unknown. So I've just got this catch here. So if I now do this, you can now see we've got A's, etc. I'm going to do the same thing with treatment. If we look at treatments, you can see you've got 1, 2, 3, 4. And again, I think it's confusing. I want to use A, B, and C, so I know it's a factor. It's nice and easy. But so I can tell between poison treatment, I'm going to call this lowercase a, b, c, d. So let's run that command. So in the first case, this poor animal was given poison A, it was given treatment lowercase a, and basically it was 0.31. The other thing you do if you find that still confusing, you could call this I, V. But next thing I want to do is you look at the top here and see it knows that this is a double, which is a numeric. It's a character, this is a character, so I want to make sure it knows that they're a factor. So I'm going to mutate. I'm going to say, look all across all your columns. Anywhere where the column is a character, convert it to a factor. So there we are. Now we've got factors. So before we do any sort of modeling, we do EDA. EDA stands for Exploratory Data Analysis. So let's do it. So the first thing I want to do is I'm going to do a count. And we see that if you had poison capital A and treatment lower a, there was 4 of them. A, B, 4, etc. So yeah, it's a fully factorial. We've got all the possible combinations of the poisons and the treatments. And we have a replicate of 4 within each one. Next thing I'm going to do skim. What does skim do? It's in the skimr package. And it basically gives me a quick summary. So we've got 48 rows, 3 columns. 2 of the columns are factors, 1 is numeric. For all the factors, it tells me if there's any missing data. It tells me I'm complete, they're not ordered, and there is 3 unique levels in the poisons and 4 unique levels in the treatment. It does a quick count for me on the top count. So it says there are 16 of A, 16 of B, 16 of C. When it comes to treatment, there are 12 of A, 12 of B, 12 of C, 12 of D. When it comes to my log survival, we've got this nice little histogram. There's no missing data. The mean is 0.479. The standard deviation is 0.253. And here is my min, max, median, Q1, Q3. Good. So that gives me an idea of what my data looks like, but we need to actually look at it. So what I'm going to do first of all is I always like to look at a nice quick histogram of my response variable. So it's right skewed, looks a bit unimodal, hard to say, not too bad. it'd be nice. I mean, ideally, you want your response variable to be normal, and that's not normal at the moment. It's quite right skewed. So what I'm going to do now is I'm going to do the same thing, but I'm actually going to do the reciprocal. And it's looking a bit better. It's still not a lot of data, you know. It's hard to really decide. And I'll show you later why I decided to do the reciprocal in another way. And we'll do this in the course. So, next I'm going to do a side-by-side box plot. So what I've done here is I have on the x-axis poison. On the y-axis I've got 1 over the log survival. I've said fill equals treatment, and I've got my box plots. So this is poison A, B, C. Here's the 4 treatments. Here's the 4 treatments of each one. And we're looking at the survival time. Okay? It's a bit hard to see patterns there. So what I'm going to do here is I'm going to group by poison treatment. I'm going to get the mean of the log survival. I'm then going to do a plot and add a line to connect them. What does this mean? It looks like this. So now you can see the patterns a bit nicer. You got the poisons A, B, C. This is the average you get for, in this case, it's the green line. So this is all the animals that had poison A and treatment lower A. So what do we see? First of all, the mean of the log over the one of survival goes up as you go from A to B to C. Notice how all these lines head up. You also notice that this one, the red, gives higher than the blue, which gives higher than the purple, which gives higher than the green. The other thing is, notice that these lines are not all parallel. So that's an indication there might be, the fact they're not parallel, to me says there's probably a little bit of interaction there, but we can always test that. Okay, so we've got that. Let's now do our first model. Our first model is we're just going to have the main effect poison, the main effect treatment. We're going to do 1 over that. And when we do that, let's do that, and then have a look at our model matrix. So what do we see? Well, here we see that we've got our row of ones, so our column of ones, which is our intercept. And then basically we've got 2 columns to represent poison. So if you're poison B, you get a 1, else you get a 0. If you're poison C, you get a 1, else you get a 0. And obviously the first few are poison A, so they have zeros in both these columns because they're neither B nor C. The same with the treatment. In this case, if you're B, you get a 1 or 0. If you're C, you get a 1 or 0. D, 1 or 0, etc. We've looked at this a couple of times now, but there's your design matrix. If we look at the summary, we've got poison B, poison C. So on average, the reciprocal of your log survival, it will increase if you go from poison A to poison B. Now let's do something a bit weird. First, I'm going to make myself a little function. What does my function do? It basically, if I give it a vector, it returns the mean of the reciprocal. Fine. Then what I'm going to do, I'm going to get the group A mean for the log reciprocal. So I'm going to take the poison, I'm going to filter for the ones where the poison is A. I'm going to pull out the column, so this pulls out the column log, and then I get the mean. So if I run this, say group A mean, there's my group A mean. So now what I'm going to do is I'm going to take that mean off. So here's the group mean, and there's when I take it off. So why am I doing that? Well, let's have a look at these values here for the group means. You've got 1.80 is your group mean, and then you should notice that group B, the mean is 2.72. When I take away that 1.8, I get 0.469. If we go up here, what do you see? 0.469. So remember I said that this was the difference between the mean of poison B compared with the mean of poison A? Well, that complicated calculation I've just done shows that that's true. What about the next one, C? So the mean is 3.8, the group mean is 3.8 for everyone in group C. The difference between that and the group A mean is 2. And up here we get 1.99, which has been rounded to 2. So it does seem to be doing the job. So the key idea here is that each of those coefficients is, the estimate is the difference between the group mean for that group and the overall mean for the reference group. And the reference group in this case is poison A. Okay. Does that make sense? Yes. So let me just recap. In the standard reference, when we do factors in R, each of these numbers is the difference between the mean of the response variable for this group compared with the reference case, which in our case is poison A. Okay. Now let's change it. What we're going to do is we're going to fit the model again. Same thing. We're going to have the same data, but we're going to change our contrast. The contrast is how we're parameterizing it. And now, instead of using the reference level for both the poison and the treatment, we're going to use the zero-sum contrast. So if I run that, I'm going to look at our model matrix. Now it looks different. So now what happens is, first of all, if you look at, you've got your intercept, and now this column, you are 1 if you're poison 1. You're 0 for everything else, except for the last group now is always a -1. Here, poison 2. You're 0 if you're poison 1. You're 1 if you're poison 2. If you're poison 3, you're -1 and -1. This setup basically means now that what each coefficient is we'll get to that. Let's not run it. So let's have a look at our treatments. You're 1 if you're treatment 1 in this column. You're 1 if you're treatment 2 in this column. You're 1 if you're treatment 3 in this column. But finally, where's treatment 4? Treatment 4 is the negative. We set it to -1 for treatment 4. -1 for treatment 4. Okay. So let's actually work out what's happening. Well, if we look at our summary here, now the question we have to ask is, what does this coefficient mean? Well, what does this coefficient mean? Well, the first thing we're going to do is we're going to get the mean of all of them. Notice I've used the brackets around, because let's say I didn't do the brackets around. Let's say I just ran that. It will run this command and save it as mean response. But I actually want to know what the answer is. If I put the brackets round, it automatically does the assignment and prints out the value as well. So the overall mean of log survival, sorry, I got to get right, the mean of the reciprocal of log survival, which is the mean of our response variable, is 2.622. The intercept is 2.622. So this value now is the mean, the overall mean of our response variable. Now, if we do our poison, we group, we get the mean, and we look at the difference. So again, we know that the mean for group A is 1.8. The difference is minus 0.822. So that's basically the group mean for A minus the overall group mean is minus 0.822. That's that value there. So to get that value there, that coefficient is telling us how much poison 1 is above or below the overall mean of the response variable. So it's basically 0.82 less. Poison 2 is 0.35 less. How do we get C? How do we get that minus that 1.17? Basically, you add these two numbers together and take the minus. That's where the minus came from. Why is poison 3 gone? Because once I know the mean and I know two of the values, in this case, you get the third for free. The same here. Once you know the mean and you know 3 of the values, you get the 4th for free. Let's check our assumptions. Over here. Not too bad. We could check this for linearity. Looks pretty good. Nice and random scatter. Normal looks pretty linear. That's looking good. You know, it was hard to tell the histogram, but that looks pretty good. Homoskedasticity, that line's reasonably level, not too bad. Leverage plot, no obvious points sticking out in the leverage plot, that's looking good. Now what I'm going to do, we'll get to this later in this course, is I'm going to take the linear model I've got and I'm going to wrap it in box Cox. Now, interestingly, this box Cox is a method. So the paper that Box and Cox wrote about these poisons, they used to develop a method. They used to to basically work out how to automatically transform your response variable to get something as close to normality as possible. And it's called the Box-Cox transformation. And later in this course, we should cover it. But let's just run it and see what it does. You get a plot like this. And what it is it's considering lots and lots of transforms. So this transform to 0 would be taking a log transform of your response variable. This would just be your response variable as is. This would be taking the square of your response variable. And this one's taking the reciprocal. This would be taking the reciprocal of the square. What you do is you look at this plot and you've got your two, what we call confidence intervals, and you find the value that lies between them that makes sense. In this case, it's -1. So when I did that thing where I sort of went, oh, let's do the reciprocal. Oh, it looks pretty good in the histogram. I didn't need to do that. I could have used this Box-Cox transform and it would automatically tell me, actually, what you should do is take the reciprocal. Okay? So there you are. There's a nice example of how you can actually, the two different codings of your categorical variable. We've had our first exposure to a Box-Cox transform. We will do this in a lot more detail later. And we had a nice look at a bit of a sick data set, but a nice simple data set to get the idea. Okay? All done. See you next week.